I'm calling this chapter Applied Electronics because we're going to take some of the stuff we learned in the previous chapter and use it to answer questions that you're going to come across when you're installing solar power systems. I'm also going to teach you how to use a volt ohm meter. Very good tool to know how to use. And how to solder. You may not need to solder, but you're going to learn how to, and you're going to learn how to do it correctly. In this next section, you will learn general test meter operation. I'm going to cover the whole meter. For solar use, you only need to know how to measure voltage and amperage. That's the current. So focus in on these aspects. Later on, though, you may find that you need to know the other features on the meter. We're going to take a look at a VOM, what we used to call a volt ohm meter. Now they're called multi-testers. This is the most common type that you're going to find, which is an auto-ranging multi-tester. It's going to have a multi-digit LCD display on the top, and then have a few switches on it, and then your main selector dial over here. And this is going to allow you to select between the different things you're going to do with the meter. We're going to talk about each one. Now this is a pretty deluxe meter, but let's take a look at the kind of things that we can check with this. The three yellow selections over here, A for amps, MA for milliamps, and this little U symbol, microamps, are the three current rating areas. And we have to select between amps, milliamps, or microamps, depending on how much current we're going to be testing. So when we do use the current ranges over here, we're actually going to have the probes on the bottom go ahead and put them in the right holes for selecting that kind of reading, for a current reading. The ground is always going to stay in the common on the bottom, the COM, but the red or hot one is going to move from the one that we use for voltage over to the current selectors over here, and one of them is called, it's a 20 amp in this case, and the other one is for microamps and milliamps. So the meter just told us we had it in the wrong connection over here. This is a smart meter, but we're on the voltage scale, and that told us, oh, you're in the wrong holes. But you're going to have to, when you're reading current, go ahead and move your red probe over to the correct hole over here for reading current, either a larger amount of current where it says 20 amps or the microamps and milliamp area. Right now, we're going to put it back in the voltage. Now let's take a look at the rest of the dial over here. We can see that the first selection from the off position to the right is V for voltage. Remember, we use the E symbol as well for volts, but in this case V, same thing, voltage, and that's for testing batteries and this kind of thing. We'll show you how it's done. The next one is our ohm scale. See the omega, that Greek symbol? This is for testing diodes, which conduct in one direction. This is for testing continuity to see if a wire has a complete circuit all the way through it, and for testing the amount of ohms or resistance inside of resistors. The next one on this meter is a capacitor checker. That's the capacitor symbol, and it's for checking the capacitance and see if a capacitor actually still functions and if its value is what it says on its label. This one also has a frequency and duty cycle. We're not going to be using that at all in solar use. And this also has a temperature probe on it, internal and external, so it can actually be used as a remote thermometer. Now the first selection is voltage. We're just going to put it on the V, that turns the meter on, and then we're going to want to use our probes here, plus and minus, to go ahead and check the voltage of something. In this case, I'm going to check a AA battery. It's quite simple. So I'm just going to use the black for the negative and the red for the positive, black being on the bottom of the battery. I'm just going to hold it on the bottom of the battery and hold this on the top and see what rating we've got. The meter is an auto ranger. That means it's automatically going to know what to set itself at, sort of what it's looking at. And right now it says 1.470 volts, and that's pretty good for a 1.5 volt battery. But remember, when you're checking voltage, that you're going to put it across the plus and minus. When you're checking current, remember with these other selections here, the yellow selections, you have to put it in series where they're in line with the thing you're checking. For checking, simply checking voltage or that electrical pressure, you can go ahead and put it right across the power supply or the battery. In fact, here's a couple of leads coming from a 12 volt power supply, like an adapter for making car current, or it could be coming out of your solar panels. So I'm just going to take the alligator clip, the black one for negative, and put it on the negative probe here, and take the red one and put it on the red. And immediately the meter will give us a display, in this case 13.36 volts. And I'm going to adjust the power supply, and we can see that that voltage can go up and down. The meter's tracking it, 8.61. all the way up to 14.46. I want to set it about 12.6 volts. That's pretty normal for batteries when you're using, say, 12 volt batteries and they're fully charged. Remember, about 12.6, 12.7, that's close enough. But remember, I'm just going right across the load here. In other words, right across the wires coming in to show that electrical pressure and potential to deliver current, but it's not really delivering any current yet. Now I've got a fan over here, a little computer fan that draws a little bit of power. It runs on 12 volts. And so I know I can use a 12-volt power supply to put these alligator clips on, say a wall wart or a power supply, and fire this up because I've got it set up to ready to go. And yep. Oh, we've got to connect the black one there. And then we'll see it spin up. And if I just wanted to check the voltage, of course, I could do that very easily and know that I've got 12 volts ready to go, but I don't know how much current this thing is actually taking. And I want to know how much power is it drawing because I may be running an energy budget for my solar system and say, well, I need to power 10 of these or something. How much power do they really take? So the first thing I've got to do, I'm going to go ahead and leave the black connector connected, but I want to break the circuit and put my meter in line with it to actually test the amount of current. So first thing I have to do is go ahead and select milliamps in this case, because milli is 1,000th of an amp. Remember, 1,000 milliamps equals 1 amp. Or 1 ampere is the full word. So milliamps is 1,000th of an amp, and microamps, that third one with the little U shape, is 1 millionth of an amp. So I'm going to take my connector first off, and I'm going to go ahead and throw it into the current, one of the current holes over here. In this case, the MA one. It's quite clearly marked on the bottom of your meter. And to put it in the MA position over here. And now I know that when I hook up the meter, I can't put it just across the positive and negative leads. I actually have to put it in line. So what I'm going to do is go ahead and take that plus from the power and connect it up to the positive probe from the meter. And then I'm going to take my negative probe, remember that, and put it where the positive one was going to go in line with the fan. And when I do that, well, there the fan starts to get its power. But also what I do see is, look, the meter is showing us how much current. In this case, well, it looks like about 217 milliamps, 216, 216.5. There we go. So now we know that this is using 215-ish milliamps, and that's actually 0.215 amps. Because remember, it's 1,000th of an amp, so 212 1,000ths of an amp equals 0.212 amps. So that's how you check the amount of current that's being drawn. Get in series with the load, and remember to have your probe into the right connector on the meter, and as well the meter in the right selection, either for a larger amount of current, amps, if you know it's going to draw more current, and it'll tell you if it's overloaded, and you'll have to switch it over to the right selection. And now our next selection on the meter is going to be the Ohm scale, and that is on an auto-ranging meter actually has 3 functions, and like I described before, if you press the select on your meter or check how you select the 3 different functions of the resistance scale, they're going to be resistance for checking resistors, and continuity, which means if you just put the probes together, you do get that little beep, and that can tell you that you are getting a conduction between these 2 things. So we'll start with that, and that would be, say, taking a piece of wire, or say you had a whole bunch of wire going down to your panels, or you had a big hunk of wire that you were going to use for your panels. You want to see that it is good, and or an old guitar cord, you know, for an electric guitar or something like that, just to be sure that it actually, the wire isn't broken inside of it. So what you do is, of course, take one of the probes and put it on one side of the wire, and take the probe and put it on the other side of the wire. And if you hear that sound, you have a good piece of wire. There is continuity, as in continuous through the whole wire. A really handy function for continuity is checking fuses, automotive or cartridge. Just put a lead on either end, and if you hear the tone, it's good. If you don't, the fuse is blown. So that can be used for a lot of purposes. Of course, you can't check something that's already got voltage in it. It has to be something that doesn't have any voltage in it. So continuity is a very important function of the ohms tester there. Now if I'm pressing the button to select again, and it goes into resistance checking, and you're going to see that omega symbol, that, you know, little omega thing on the screen. And I'm going to take a resistor over here. All resistors are going to have sort of this tubular shape, and they offer a little bit of resistance to the flow of electricity. And whatever the resistance is in ohms. So the meter can check how many ohms the resistor has simply by putting it across both leads of the resistor. And the meter will then tell us, oh, this is 38.7 K ohms, K for 1,000, 38.4 kilo ohms, 38,700, something like that, about like that. And if I was to go out and look at my resistor color code, you can look that up you can Google that. You can find out what the color bands mean to make sure that this one is supposed to be that amount of ohms, 47,000 ohms. But I can tell you right now, if you see a short circuit, it reads all zeros across the meter. then this resistor is burned out, especially if you see it burned out. That's a good way to tell it actually will physically burn. So if it reads absolutely no ohms, it's open circuit just like now where it just says nothing on the meter, OL, or if it reads all zeros and doesn't come up with a number, that resistor is bad. Right now, bam, we're at somewhere in the mid-scale, 42.4 thousand ohms. And different resistors, of course, have different color bands, and they have different values. And they're used to add a certain amount of resistance in the circuit. 987 ohms in this case, and that's close to, it's supposed to be 1,000. That's pretty darn close. So I'm going to press it again, and then we get to the diode check. Diodes are things that look like this. They've got a band at one end, and they only conduct electricity in one direction. And you can easily tell that you put your plus on the end that does not have a band and put the black on the end that has a band, and you should read from 0.4 to 0.7 on the meter. If you read all zeros or if you read nothing like overload, that diode is bad. So I'm just telling you how to check these very, very basic electronic components on a circuit board, say. Just put the meter across them in this mode, diode mode, where it shows the diode symbol on the screen, and bam, you've got to read what we call a junction. There has to be a little bit of a voltage drop inside of that diode for it to function. And again, it's the red on the non-banded side. You'll see these little tubular diodes with a band on one side, the cathode it's called, and the anode. So there we go, all the functions and features of the resistance scale, and that continuity being a very important one to check things to find out if there's a complete continuous circuit path inside of a wire or something. Our next selection on the meter is the capacitor symbol for capacitance to check capacitors. And a lot of capacitors are going to look tubular like this, but there are a ton of different varieties. There's more variety in capacitors than there are in any other electronic component. They all come in different kind of shapes and forms. You just never know what you're going to see out there. But they all have markings on them that indicate they are capacitors. These little tubular electrolytics over here are very easy to check in the capacitor scale. It has a negative marking, a negative band on it, and also the longer leg, if it was not in a circuit, is the positive. I'm just going to put the meter across it, and bam, it comes up, let's see, 4.77 UF, that's microfarad. Well, this is a 4.7 microfarad capacitor. It says right on it, 4.7 UF. So I know this capacitor is good. Again, if it was a short circuit, all zeros, or OL for overload, and we weren't getting any numbers on it, this capacitor would be blown out. Some of them do not have pluses and minuses on them because they're not polarized capacitors, and you can check those the same way, but it just doesn't matter what lead is on what lead of the capacitor. So again, we're reading almost exactly 500 microfarads here, and that's exactly what this is supposed to be. So it's not all zeros, and it's not, it's giving me a nice mid-range reading. That means that the cap is probably good. But you won't find yourself checking any capacitors unless you're troubleshooting circuits in normal solar power work. Just want to tell you how to use it. Now your meter may have a temperature scale on it with a separate temperature probe. They sort of come with probes that look like this. They plug into the meter, and then you can take this little probe end and stick it on, you can check the temperature of a wood stove or some other thing to see if it was the right temperature. Sort of a handy item, and a lot of these multi-testers these days have these temperature probes. This one as well, the X-Tech, has a built-in infrared thermometer, comes out of the top of the unit, and pretty handy for checking temperatures at a distance. So most of the time you're going to be using your volt scale for V. And remember, there is a little fuse inside of these. There's usually a 9-volt battery or batteries to power it, and there's a little fuse. And if you put too much current in one of the current areas over here, all of a sudden it won't read anymore, and you will have blown the little input fuse. The fuse protects the meter from being blown out if you were to put a whole bunch of power through it. Remember, again, voltage is across, just plus and minus, looking across the wires, and using current for amps, milliamps, or microamps, you've got to change that probe over to the current area. Put it in the 20 amp, you're really reading a lot more current, and then go ahead and put this in line or in series with the thing which is drawing power to tell how much power it's drawing. And remember, volts times amps equals watts, the true amount of power that you're using. This is a clamp-on type of multi-tester, really good for solar applications because it has a clamp at the top, and rather than having to break the circuit to get your current readings, you can just put it around the wire, say coming down from the panels, one at a time around the red wire, and sometimes the black will work, and it'll give you your current reading right on the LCD display. Plus, it also has the standard probes, and we showed you how to use those for doing your voltage and resistance readings. Well, here we are at one of our small solar battery systems, and I'm going to use the clamp-on meter to show you how easy it is to use. What's great about the clamp-on meter is, for current readings, where you would go ahead and have to break the circuit and put the wires in series with the circuit to see how much current was going through it, well, we don't have to do that now because we have the clamp. This has the wires, so you can use those too if you need to. But the clamp is great because, well, here's our charge controller over here, and all I have to do is clamp it around the positive wire, and then I can just read the meter and see what it's actually putting out. I don't have to break the circuit, which is just tremendous. Or I can go to, say, our output breaker over here and say, well, how much power is going into the house? And just clamp it right around the positive leads going out, and we can take a look at the metering on that too. So anywhere you've got a positive wire run, I have an auxiliary battery bank over here that's saying trickle charge. I can pop it around that positive wire and get a reading. Well, how much power is going over there without having to break the circuit? That's what's great about these clamp-on meters. I want to mention a shunt to you. This is an electrical device, and a shunt is physically just a bar of metal with two connections at the ends. It has a very low but known resistance. Now, it's connected in series at the end of a negative wire in a circuit in order to allow you to tap off a sample of the electricity and display it on a meter. Now, because there'll be a slight voltage drop across the resistance, that shunt has a little bit of resistance, it's like a resistor, and that change in voltage from one side to the other will go up and down with the amount of current going through it. That's our Ohm's law. A meter can interpret that voltage change from one side to the other of that shunt into an actual current passing through the shunt. It's a way to tap off and tell you how much current is going through that circuit. But since the newer components we're going to be using already have nice LCD displays on them to show us our current and voltages all around the system, you most likely will never need to use a shunt. But you may come across one in an older setup, and I don't want you to not know what it is. And here's what they look like. Notice that there's very small wires attached to the left and right part of it, the blue and red connections. Those are just tap-offs going to the meter to just take off that little bit of voltage and display it on the meter. And of course, these are connected at the end of the black wires to that big grounding bus on the left, the piece of brass. Don't concern yourself with these too much because you'll probably never install one. So I'm now going to show you the correct way to solder. A lot of people think they know how to solder correctly, but it actually is a trained skill. So the first thing to know is that you want a clean soldering tip. And that means that the tip of the gun has to be absolutely, or iron has to be absolutely clean. You can use a little sponge, a little bit of water in it, keep that handy, and keep that tip nice and clean. Plus, you're going to want to tin the tip. In other words, once it attains its heat, you have to add a little solder to it and get a little bit of solder on that tip. And be sure that there's a nice clean blob of solder, and then you clean it back off on your little wet sponge, and you're ready to go. And also that the soldering gun must be the correct wattage, because if you try to use the wrong wattage gun, you're going to be very frustrated. It will not work. For wires, say, of this size here, a 10 gauge or smaller, a 30-40 watt soldering iron will be just fine, a little soldering pencil gun. If you're looking to solder Romex or larger wires together, you're going to need a soldering gun, this type of handheld gun over here, more like in the 140 watt range. So the next thing to know is that your work, we're going to call this the work, the wires itself, has to be clean. And if it's not clean, it will not accept the solder. So flux is what is used to clean off the work or the wires as the solder is put on. And a lot of solder has the flux built right in. Now, the kind of solder you're going to use for electrical work has to be electrical solder. It cannot be the kind used for plumbing work. So there are two different types. And the stuff used for electrical soldering has the flux or rosin built into the center of the solder itself. Sometimes it's called rosin core. So then, now for our technique, remember that your work has to be mechanically secure. In other words, it has to be twisted together in a fashion that it would hold itself already without the solder, because you don't have a third arm to hold it together. I'm using an alligator clip stand here to hold the wire, but your work has to be mechanically secure before you solder. Then when you're soldering, what you do is put the tip on the contact of the work and the tip here, and when you start, you put a little bit of solder right on the contact point, right where that tip is touching the work, and wait. Don't blob a whole bunch of solder on. Now is the patience part. You're going to wait, you're going to sit there, and count to 7 or 8, something like that. Watch the work, because you'll see when things are happening. You cannot conduct heat into the wires, again I'm calling this our work, unless there's a little bit of solder right there between the tip and the wires. Now as soon as you really start to conduct heat, you'll notice it'll start to smoke a little bit. Then you can start to add a little bit of solder, and you'll know that it's up to temperature because the solder will then wick into the wires. If your soldering gun is inadequate in size, it will never get the wires hot enough to accept the solder. And now look, all the way up the way here, I'm able to add the solder. Take the solder away, count a few seconds, and take the soldering gun tip away. If the connection is good, the solder will have sort of a shiny look to it. If it does not, it looks a little bit dull, you may have what's called a cold solder joint, and there may be little fractures in it. You didn't get a good contact. So you have to go in and reheat the work. Again, patience, patience, patience. When it's heated up enough, try to get a good amount of contact between the tip and the wires, add a little more solder and reflow the connection. And when it's sort of looking shiny, give it a few seconds, pull away, you've got a good connection. Now I'm going to show you how to make a connection insulated from the outside world. Say we have our two pieces of wire soldered together. Right here, and here's the solder point over here. Well, we're going to add a piece of heat shrink. And that's this material over here. It looks like this. It comes in different diameters and different colors. And basically what it is plastic tubing that shrinks when you add heat to it. So instead of using electrical tape over a connection, you can go ahead and use a little bit of heat shrink over it for an even more professional cover to the wires. So I'm going to take a piece of this heat shrink and just cut about a 2/3 of an inch piece here that I might use on enough to cover up the connection on both sides of the metal so that it's not touching anything. And I'm going to take my little piece of heat shrink and slip it over the wire and slip it over the connection so that there is a little bit of excess on both sides over here. Then I'm going to use a heat source. In this case, I'm going to use one of these little butane fire starters things that you start fires with for fireplaces, this kind of thing. And I'm just going to fire it up and quickly put it around here. Now I could use a very high power hair blower on this, or specific tools that are made for shrinking heat shrink, but these things work just great. So, you know, a couple dollars and you're ready to go. And there we go. We have a completely insulated connection now, professionally done. Again, electrical tape works fine, but this is really even a better way to do it. I suggest a little break at this time. You've earned it. You've learned a lot about electronics so far. So take a little break and then come back and continue with the rest of this chapter. Now for something really exciting. Our first complete overview of a battery backed up solar power system. Now don't worry, we're going to come back and review each one of these components and tell you everything about them, but you need to just take a look at the overview first and then it will come together for you later. On the top left is our photovoltaic array. It has all of the panels wired together, and sometimes you use a combiner box right after that to combine all the wires from the panels. Then the wiring comes down with that power to a disconnect where you can turn the array off. You can pull a plug and turn the power off coming in from your solar power array. Then we're going to run wires, that's all the red lines, over to a circuit breaker, and that means we can flip a circuit breaker switch and turn things off. We always add circuit breakers between all of these components. And then it comes out of the circuit breaker and goes up to a charge controller. And this is the intelligent brain, the little device which charges your batteries and makes sure that it's the correct voltages and currents and keeps your batteries healthy and fully charged from the power coming from your solar panel array. Then we go through another circuit breaker box where we can turn that circuit breaker on and off and disconnect power, and then into our battery bank where the power is stored. That's pretty self-explanatory. Then it comes out of that and into another circuit breaker where we can turn that off right at that point. We can disconnect at any point, and then into our inverter, which takes the low voltage battery power in DC and converts it into AC power. Then it comes out and goes through another circuit breaker box with some regular type of AC circuit breakers, and then into your house for powering different AC appliances and such. So these are all the components in the system, and we're going to go ahead and tell you about each one in detail, and all of a sudden you'll really get the concepts and it'll come together for you. And now I'd like to talk about kilowatt hours, a term that you hear a lot, but I'd like to show how it applies in solar energy systems. A kilowatt hour is simply 1,000 watts used for 1 hour. That's 1,000 times 1. Here are some examples of a kilowatt hour of energy being used. Say a 1,000-watt hairdryer used for 1 hour, or a 500-watt heat lamp used for 2 hours. That's still 1 kilowatt hour. Or a 250-watt stereo used for 4 hours. 4 times 250, 1,000, 1 kilowatt hour. Or 10 100-watt light bulbs used for 1 hour. Or 70 high-efficiency fluorescent screw-in bulbs for 1 hour. That's also 1 kilowatt hour. So knowing what we know so far, we can start to put together an energy budget by adding each appliance we want to use by its watts and its hours of use per day. A lot of times these appliances will have a small label on the back where it shows the actual amount of wattage draw, so get that number off there. And let's say we had 5 high-efficiency fluorescent bulbs we were going to use for 4 hours in the evening every day. That's 5 times 13 watts each, it's printed on them how many watts they draw, equals 63 watts of draw continuously, times 4 hours equals 252 watts per an hour. So it's as if you use 252 watts for only 1 hour, but that is actually 0.252 kilowatt hours. The next, say, one big 40-inch flat screen TV, it draws 200 watts, it says on the label. You're going to use it for 5 hours in the evening, so that's 200 watts times 5 hours equals 1,000 watt hours, or 1 kilowatt hour. And the last, a deep freezer at 750 watts, but it only runs about 25% of the time. The compressor only comes on about that amount of time per hour. So 25% of 24-hour day is 6 hours times the 750 watts that it draws equals 4,500 watt hours, or 4.5 kilowatt hours total. You can see how you could go around the house and start to add up exactly what your energy uses are going to be, and especially if you have a proposed setup for solar power, say in a cabin or a small house, you can put an energy budget together this way. Here's what I call a hit point, something you need to memorize. 6 watts of photovoltaic power from your array will produce about 1 kilowatt hour of electricity per month with over 6 hours of direct sunlight a day on the array. So that means after you get about 6 hours, 7, 8, you might do a little bit better than this. But with an average of about 6 hours, maybe a little bit more than that, you're going to start to really accumulate about 1 kilowatt hour of electricity a month for every 6 watts that your photovoltaic array puts out. Lastly, let's use our power formula, volts times amps equals watts, to figure out how much power is coming in on this small system during a cloudy day. The controller display is showing us 13.4 volts and 4.1 amps. So if we multiply 13.4 times 4.1, we got 54.94 watts coming in from this system on a cloudy day. Pretty easy to figure out. We've learned a lot in Chapter 5. Let's review. Number 1, you can use a VOM, that's a volt ohm meter, or commonly called multi-tester, to check volts and amps and all the different electrical values that we've talked about. Your tester leads are in parallel to look at volts right across that positive and negative, and your tester leads are in series with a load to test amps or current. Clamp-on meters go around the hot wire. You don't have to break the circuit, so it's very convenient. Soldering correctly is a learned skill. Just follow the directions. A solar power system has 5 major components. Remember the solar panels themselves, the charge controller, the inverter, the batteries, and all of your circuit breakers. A kilowatt hour is 1,000 watts used for 1 hour in any combination. So you can come up with a solar energy budget